Today we're going to look at support vector machines. I'm going to start by giving the motivation for this kind of classifier, which is to try to maximize the margins, the distance between the points and the discriminant. And then I'll talk about what the support vectors are and start a bit into the mathematics behind the support vector machine. This is going to be a bit dense and perhaps a bit confusing, but the basic idea is so that you understand why the function that we optimize to fit this classifier at the end has the shape that it does. Because then there are some interesting properties that we're going to look at in the second block today that depend on this function here. So first, let's look at this idea of maximizing the margin. We saw when we were trying to build a classifier initially, we saw this example of two classes of cells, tumor and normal cells, and we have two features which are the gene activities that I'm representing here in the two axes. And depending on the gene activities, we can separate the classes of cells between the tumor cells and the normal cells. First, we tried to create a classifier that would fit this quadratic error function to predict a class -1 and 1 for either of these two classes. But this didn't work because this quadratic function makes it so that points that are far away from the discriminant pull the discriminant towards that side, and so our separation is not in the correct place. So this was an incorrect approach, but it gave us an important insight into classification. And like regression, we don't want to fit the line close to the points. Rather, we want to identify this critical region here where the line must separate the two classes, and actually the rest of the points don't really matter. Only those that are close together here are important for determining where the separation is. So with the logistic regression, we use the logistic function. We're trying to do a regression to probabilities, and we solve this problem implicitly by using this logistic function that tends to level away into a constant value away from the frontier, away from the discriminant. So actually, with the logistic function, we go from one value here to another value here. Everything that is far away from the discriminant has the same value or nearly the same value, and only here where the logistic function has that step, goes from low to high or high to low, only here does it make a difference where the points are. So this allows us to create a classifier that works. We use a regression to the probabilities, but then cut at the point of equal probabilities for each class, and we can make this work like this way. One problem, however, that we found is that if we increase the magnitudes of our parameters, so the vector that defines where this hyperplane will be, then we can arbitrarily increase the steepness of the logistic function. And if the logistic function is very steep, it becomes rather loose. We can put it anywhere between the two classes and it will not make a difference. So this results in a problem of overfitting, if our model is overfitting, in that we can approximate the discriminant arbitrarily to any of the points without increasing the error in the training set, but then this may give us problems when we try to predict values outside the training set. So what we did with regularization was to impose a penalty on the size of the coefficients and try to make the logistic function increase more slowly, so make it less steep, and this forces the frontier to move away from the closest points. And this is an important idea. We want to avoid this problem of having the discriminant very close to the points. By moving the discriminant away from the points, we minimize the probability of making mistakes outside the training set, and so we are trying to mitigate any problems with overfitting. So in other words, we want to maximize this margin between the discriminant and the closest points. So with regularization, the function becomes smoother, and we force the discriminant to move closer to the center here between the two classes and to move away from these points that are closer to the other class. So this is what regularization does. It minimizes overfitting by constraining where the discriminant can go. So if we move the discriminant further away from the points, we can mitigate the problem of overfitting. So this is an important idea that with logistic regression we managed to do by changing the loss function. So this would be a possible implementation. We receive the coefficients here. We compute the dot product between the coefficients and our data so that we can compute this part here of the expression. So this is the dot product between the vector of coefficients and the matrix with all the data, and we add this constant so we can compute this for all the points. Then we pass this through the logistic function and we compute the cross entropy here. So by taking this expression that we're trying to minimize here. So this would be to try to find the best place to put the discriminant. However, we change this loss function by adding this penalty, which is the sum of the squares of all the coefficients divided by this C parameter. So this is what the logistic regression classifier does when you use it in sklearn, that adds this penalty function here that depends on this C parameter that we can regulate. If the C is very high, then this term becomes increasingly smaller and less important. If the C is low, then this term increases and becomes more important. But the problem here is that this feels a bit like cheating. We are changing the cost function to impose regularization to do something that we could try to do explicitly, which is increasing the margin. So this is where this idea comes, the idea of the maximum margin classifier. We have a margin classifier if we have a classifier that allows us to compute a distance between the discriminant and each point. So we can measure the distance the point is away from the discriminant. And a maximum margin classifier is one that actually, when it's fitting the model to the data, is trying to maximize the distance between the discriminant and the nearest points, so that we can move away from the nearest points. We won't put the discriminant here close to the blue points or here close to the red points, but rather we put the discriminant as far away as possible from the closest points. And these closest points, which are the ones that determine where the discriminant must go, are called the support vectors. They are vectors because they are vectors of the features, and they support the discriminant, they force the discriminant to be there. So this is an important concept because, you see, if we determine the discriminant by moving as far away as possible from the closest points, then everything else in our data is really irrelevant. It doesn't matter where these points are, as long as they don't come closer to the discriminant than these three, then the discriminant will be always exactly here, because it's stuck in this place by the position of these 3 points. And this is really the intuition that we're trying to capture here. What matters to separate the two classes are the points that are closer to the other class. Everything that is farther away on the correct side of the discriminant is irrelevant because of the place we need to cut. That place won't change because of the other points. So if we move this point over here or over there, it would make no change to the discriminant. So this is the notion of the support vectors, those that fix the discriminant when we are trying to maximize the margin. And this is a basic notion in support vector machines. But let's try to implement this. In theory, it should be easy to implement this because all we need to do is to look at the closest points and try to move the discriminant away from the closest points. So let's try to do that. This will not work, but we'll see why it doesn't work, and it will allow us to get a clearer idea of our goal in this case. Let's consider the signed distance to the hyperplane. So this set of parameters, the parameters that we're trying to fit, are the ones that determine where this hyperplane lies. So in 2 dimensions, this is only a line. In 3 dimensions, it will be a plane. In n dimensions, so for the general case, it will be a hyperplane. But it is perpendicular to this vector, and this additional constant determines if it's more up or down on that axis. So we can define this sine distance to the hyperplane by using this value, which is the inner product between any point and this vector here plus that constant, which will be positive on one side of the plane, negative on the other, and we can normalize this by dividing by the size of this vector, so that we can actually measure the distance in the same units regardless of how large this vector is. So this sine distance will tell us the distance to the hyperplane in a way that is positive on one side of this hyperplane, negative on the other. And now, to maximize the margins, what we want to do is to find the parameters for our hyperplane that give us the maximum value to the minimum of the sine distance of each point multiplied by its class. So the class here can be -1 and 1, and if the point has a class of -1, it must be on the negative side. If it has a class of +1, it must be on the positive side. So we will take the smallest value there, which means the point that is closer to the discriminant, and we want to maximize that one. So when we look at this picture, what we want to do is to place this line in a way that maximizes the distance to the closest points. We don't care about the others. We only care about the points that are closer to the discriminant. So this is actually very easy to implement. We create this loss function here that receives any set of parameters, the features, and the target classes. The classes are -1 and 1. We create here the vector, which is a column vector, so that we can do this dot plot here between the matrix with all the features and the vector. By the way, this flatten here is probably not necessary, but just to show you that this is the inverse of this operation we're doing here. So here we are creating a matrix and filling the column with the values. This is useful when you need to take some vector and give it a bidimensional shape as a matrix. This is doing the opposite, which is taking something that can be a matrix and flattening out into a vector. So sometimes you need to do these operations, flatten a matrix or convert a vector into a matrix. This is just to give you an idea of how you can do that. But the point here is rather simple. We are computing in this expression, we are computing this expression here, which is the dot product between the coefficients and the features plus this constant. And we then divide by the norm of the vector, which is simply the square root of the sum of the squares of the coefficients. And this is the distance that we're trying to maximize here. So the smallest distance is what we're trying to maximize. Now, because we actually have to use the minimize function from SciPy, we need to change the sign, because if we want to maximize the smallest distance, we want to minimize the negative of the smallest distance. But basically, with these few lines of code, we can implement this expression here, trying to maximize the smallest distance to the discriminant. And when we run this, we can start with a random set of parameters and then minimize from there. And if we run this several times, we just get garbage. So this is very simple to implement. It's very intuitive. We're trying to find the position of the discriminant that maximizes the distance to the closest points, but it doesn't work. And the reason why it doesn't work is not the theory is sound, but it's the numerical problem of trying to optimize this function. So this is a representation of the distance to the closest points. And what we get is these smooth quadratic functions. So as we change the parameters, we are changing the distance, so we have these smooth curves. But at some combination of parameters, the closest point stops being one and starts being another. So if you imagine here, if we are moving these, for example, changing this line, changing the orientation of this line, then at some point this vector here, which is closest to the line, may be replaced by another vector here that becomes closer because the line is now at a different inclination. And so at these combinations of parameters where the closest point changes, we have a discontinuity on the derivative of this function. So the function is continuous but has these sharp edges here where the points change. And actually the maximum value here will be one where we have several points at the same distance from the discriminant. So the maximum will be exactly on that sharp edge. And since these minimized functions, these optimization functions, must depend on the derivative to try to guess the next value, if we have a discontinuous derivative, they don't work. So that's why this minimization will not produce any useful result, because it's impossible for that numerical algorithm to find the optimum when the derivative is discontinuous. Okay, so this is the motivation for the support vector machine. We know what we want. We want to maximize the distance to the margin, maximize the distance to the discriminant, that is, to maximize the margin, because the margin is that distance between the closest points and the discriminant. However, this leads us to a function, a loss function, that has discontinuous derivatives because the closest points can change as we change the parameters. So we cannot solve this directly. We must go now in a roundabout way to try to solve this problem. So this is what leads us to the support vector machine. The basic idea is simple. We want to maximize the margin, and the margin is determined by those support vectors, by the examples in our data that are closest to the discriminant. We cannot compute this easily because of this discontinuity in the derivative when the points change as the discriminant is changing orientation. So now I'm going to show you a lot of equations. These I'll show just the minimum necessary for you to understand why the support vector machine has that expression at the end, because this will be important to understand its properties. So I'll skip a few steps in the demonstrations. And the idea is not for you to memorize. I will not ask you to demonstrate this or write the expressions. This is just to understand what is a support vector machine and what we are trying to optimize, what are the parameters that we find, and why it has the properties that it has. Okay, so let's change the problem we're trying to solve. If we look at the normalized distance, the reason why it's normalized is to make it invariant to the scale of the size of the parameter. So if we increase the numbers of our parameters by the same factor beta, this will also increase the size of the vector, of the coefficients, so the distance, the sign distance, will be the same. Now if we define the margin as being only this part here, so this product of the class and the inner product of these coefficients and the features and so on, we can guarantee that as long as the classes are separable, we can make this value at least as large as 1 for all the points just by changing the size of the coefficients. So if we compute this value for all the points and we realize it's only 0.5 in some cases, then we just double the size of our parameters and we can make this at least 1 for all the points. So we just rescale everything and we can impose a margin of at least 1 for all the data in our training set. And now if we guarantee this condition, if all the data in our training set has a margin of at least 1, in that case maximizing the smallest distance will be equivalent to minimizing the size of our coefficients. Because if we minimize the size of our coefficients and we still maintain the distance of at least 1, then we must be moving the discriminant away from the closest points as much as possible. So this is the basic trick here. We impose this constraint that the margin must be 1 for all the points in the training set, and if that constraint holds, then we get the same result. The same result of maximizing the smallest distance can be obtained by minimizing the size of our coefficients, as long as this constraint is respected. So this is useful because now this expression is a lot easier to minimize. It's simply a quadratic function. It doesn't have those edges, those sharp edges and discontinuities in the derivatives. The problem now is that we need to enforce this constraint. If this is not true, then this doesn't work. It only works if we can make sure that all points have a margin of at least 1. So let's see how we can do this. We have a constrained optimization problem. We're trying to minimize this expression subject to these n constraints. Note that there are as many constraints as there are points in the training set, because this must be true for all the points in the training set. And this we can solve with this method of Lagrange multipliers. So now I'm going to take a small detour just explaining what Lagrange multipliers are, because what we get in the end are these Lagrange multipliers, and we need to have some basic idea of what they are in order to understand what the support vector machine is and how it works. So let's look at this simplified example. Suppose that we have this quadratic curve here as a function of x and y, and we want to find the point, the combination of x and y that maximizes this value. However, we want to find it subject to this constraint, x minus y minus 1 equals to 0. So we have this function equals to 0, and this gives us this line here, and we want to find the maximum for this red surface subject to keeping the x and y values on this line here. So this is where we are looking at the maximum value. Now if we find the maximum along this line, at the maximum, the function cannot increase in the direction of the line, because if it increased, then it would not be the maximum along the line. So we are going up, 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 and then we cannot go up anymore. This means that at the point of the maximum, the point that we have here must also belong to a contour line of the function we are trying to maximize. So if we go along the constraint and find the maximum there, we reach a contour line of the function to optimize, and the contour line is simply a line where the value of the function is constant. So at the maximum along this line, which is along this line here, the maximum of the function we're trying to optimize must belong to a contour or line here. So the constraint that we are applying must be parallel to the contour line at the maximum. So this is an important idea, because now we can look at the problem that we are trying to solve here as the constraint optimization as the combination of two functions. The function that gives us the constraint, which is this g of x and y equals 0, this function here, which is the one that gives us the constraint, has a contour line, is a contour line of function g. So it's a line where this function is constant. And at the maximum of f, the one we're trying to maximize along this line, the maximum is also part of a contour line of x, of f, sorry. So at the maximum point is both part of the contour line of g, because all the constraint there is part of the contour line, and it's part of a contour line of f. So basically, the contour lines here are parallel, which means that the derivatives must also fall in the same line, because the derivatives must be perpendicular to the contour line. So you can see that the contour line is the line where the function is constant. So if the function is constant, the derivative along that line is 0, and the component of the derivative along that line is 0, so the derivative must be perpendicular always to the contour lines. So we know that when we find the maximum, the combination of xy that maximizes f subject to this constraint on g must be at the point where the derivative of x of f as a function of xy is on the same line or parallel or anti-parallel as the derivative of g as a function of xy. So we can write it this way. The derivative of x at that point must be some alpha multiplied by the derivative of g. So in this case, the minus sign there is just conventional, because the alpha could be anything, and so it's conventional so that we can pass this term to the same side as that one and get a sum like this. So this is how we define the Lagrangian. The Lagrangian is simply the sum of the function we are trying to optimize plus some alpha multiplied by the function that gives us the constraint of the form g of something is 0. If we add these two and then we solve for when the derivative as a function of x, y, and alpha is 0, we find the critical points of the Lagrangians, and we know that the solution to our problem, which is to maximize this one subject to this constraint here, must be in one of those critical points, because it must be in one point where this is true, where the derivatives are the same. So back to our example, we can solve this by finding the value of x and y for which all the derivatives of the Lagrangian, so this is the Lagrangian here, it's the function we're trying to optimize plus alpha multiplied by the function that gives us the constraint. This equals 0. If we solve by finding the derivatives as a function of x, y, and alpha, with respect to x, y, and alpha, all these derivatives to be 0, so the derivative of the Lagrangian with respect to x is this value here. This is with respect to I, and this is with respect to alpha. And if we solve this system of equations, we find that x must be 0.5 and y must be minus 0.5. So this is the critical point we found for the Lagrangian, and it gives us the solution to the optimization. So in this case, it's this point here. It may happen that the Lagrangian has more than one critical point, and we may have to test them to see which one corresponds to the maximum, but this is how we solve this kind of problem. Okay, so the reason why I made this detour is because we can now apply the same method to our problem. Our problem is to try to minimize the size of the vector of coefficients by while keeping this constraint true. So for all our points, the margin must be at least 1. This is the same as writing that for all our points, this expression here must be 0 or less. So this Lagrangian method also works for these kinds of inequations, and we can write now the Lagrangian for solving this problem. So we have the function we need to maximize here, and then we add all the alphas multiplied by the function that gives us the constraint. So since this has a negative sign there, we can just put the negative sign outside the sum. And this sum here sums over all our data points, because this constraint must apply to all the data points in the training set. And now we have this sum for all the points in the training set. We have for each one Lagrangian multiplier, and multiplied by this expression here. So at the critical points of the Lagrangian, all the derivatives are 0, and we can compute this, the derivative of the Lagrangian with respect to the direction of our hyperplane, so the direction of the vector that defines the hyperplane. If we solve for the derivative of the Lagrangian being 0 with respect to that vector, we have this expression here. So at the critical points, the sum of all the Lagrangian multipliers multiplied by the class of the corresponding points and their features must give us the vector with the direction of the hyperplane. We do the same thing for the W0 here, and we get this constraint for the critical points, which is the alphas, the Lagrangian multipliers multiplied by the corresponding classes must add up to 0. So this means that if we have Lagrangian multipliers for class 1, we must have the same amount or the same total of Lagrangian multipliers on the class -1 to even things out here. And now we can replace these conditions in our expression, and actually there is a more complex step here, but we can find a dual representation of the problem, which is basically a representation that gives us the same answer at the end. And this is the final shape of the support vector machine. So you don't need to memorize all these steps, but it's important for you to understand what these alphas are. So these are the Lagrangian multipliers that come because we are imposing a constraint on all the points on our training set. All the points on our training set must have a margin of at least 1. So we have one Lagrangian multiplier for each point in our training set. And then we're trying to find the set of Lagrangian multipliers for all our points that maximize this expression. The sum of the Lagrangian multipliers minus 1/2 this expression here, which is summing over all combinations of points, the product of the two Lagrangian multipliers, the product of the classes may be 1 or -1, and the dot product, the inner product of their features. And we are trying to maximize this subject to these constraints. All the Lagrangian multipliers must be at least 0, and we have this additional constraint that that came from here, that the Lagrangian multipliers multiplied by the classes of the corresponding points must all add up to 0. So intuitively we can understand this expression, the expression that we're trying to optimize in this way. We're trying to make the Lagrangian multipliers as large as possible, and if we find points that are far away from the frontier, so this means that points that are similar to each other and they have the same class and they are close to each other, then if they have the same class, this product will be positive. If the points are close to each other, the inner product of their vectors on the features will also be positive because the points have similar features. And so this term here will be positive. Since the Lagrangian multipliers are positive, we are actually penalizing this function if we give large values to these Lagrangian multipliers. So the best thing to do is to give values of 0 to Lagrangian multipliers of points that are far away from the discriminant and only have neighbors of the same class. If we have points that have neighbors of different class, then this product here will be negative because one of the points will be class -1, the other will be class +1. And since the points are close together but they have different classes, this will be a positive value, the product of the features. This will be negative. And so since we are subtracting a negative value, this is good for maximizing this expression. So if we find points that are close together but they belong to different classes, then it's good to increase the Lagrange multipliers for those points. So basically what the Lagrangian multipliers here will tell us is which points are close to the frontier between the two classes. So these are the support vectors. Those that are away from the frontier, the Lagrangian multiplier will tend towards 0, and this will be irrelevant for classification. So this is the reason why we call this a support vector machine. We're actually, when we optimize this function, when we maximize this function, we get Lagrangian multipliers that are 0 for all the irrelevant points and larger than 0 for those vectors, for those points that are that are forcing the discriminant to be in that position. And this we need to solve subject to these constraints, but this can be solved with quadratic programming. So I'll just give you a quick example of how we could implement this. So this is not for you to implement because you're going to use the support vector machine from scikit-learn, but it's just to point out that we can decompose this into different parts. So one thing we can take out from this expression is this part here. The inner product of all pairs of examples multiplied by their classes is a constant matrix. We can compute this matrix as a constant of all these sums. So this is the example for the code here. We start with a matrix of zeros that has as many rows and as many columns as the number of points in our data set. And now we fill in all the rows and columns with the dot product between pairs of examples, so example n and example m, multiplied by their classes. So this matrix is fixed and is determined only by the training set that we have. We don't need, we can compute it once and just use it for all the iterations during this optimization. And this is an important thing because we can separate this from the rest. And now we can implement this by writing the loss function. So the loss function is this expression here, which is simply the product of the alphas and the matrix that we computed before. And then we add this term here. But note that we want to maximize this, and since we are always using the minimize function from SciPy, we change the sign here. So this is just the loss function that we're writing. In this case, we have a lot of parameters because we have one alpha for each of the points in our training set. And so we need also to give the minimize function the derivatives. But this is merely the derivative of this expression with respect to each alpha. So you get the vector of all these derivatives. And now we can use the minimize function with that loss function, with the derivatives, and adding this dictionary with the constraints. That is basically this product here. So the product of the alphas and the classes must be 0. So this is how you could implement the support vector machine using SciPy from scratch here. We first compute the matrix with all these products, the inner products of the examples, the features of the examples and their classes. And then we define the constraints that we have here. This lambda in Python allows you to create an anonymous function. So instead of just creating a function with a name and inserting there, we create the function object in place. But we don't need to go into much detail here. So basically, this is the constraint that this sum must be equal to 0. And then we have the loss function and the derivatives to help find the minimum there. And what we get in the end, when we apply this to this data set, is a set, the solution here is the set of alphas that maximize this expression. So what we get is a set of values that if we compare to a very small number, we see that most of them are close to 0 except 3. This one here, this one here, and this one here. And these correspond to the support vectors. So all the points here got their alphas very close to 0. The only 3 that have alphas that are not 0 are these 3, because these are the 3 points that determine where we must separate the two classes. The other points, being where they are irrelevant for this separation. And we can now even look at we can compute the different coefficients. For example, let's consider these support vectors. The support vectors are the vectors where the alpha computed is at least 0.01. So this is how I define here. The reason for doing this is because when you do the actual computation, so we're going to see that in the next lecture, when you do the actual computation, the zeros are not exactly zeros. They are very small values. But we can consider that everything below 0.01 is in practice a 0. And we identify these 3 support vectors. And now we can compute the coefficients from this. So if we take the support vectors, we can find the set of coefficients determining the direction of our hyperplane by multiplying the class and the features for all the values. We can use all the values in our data set, or just the support vectors, because everything that is not a support vector will have a 0 there, so it will be irrelevant. And this is why the support vector machine is now dependent only on these support vectors. Everything else becomes irrelevant because the Lagrangian multiplier for those points becomes 0. For the last parameter here, we can use the support vector and we can use the support vectors to compute this W0, because we know that for points belonging to the margin, the value for the margin is 1. So we can actually do this computation here and get all the coefficients. So there's one question: if it's possible to have less than 3 alphas different from 0. In theory, it's possible if we have only 2 points, for example, if we have 1 point in one class and in another, or if we have something in a shape there where the discriminant is actually only determined by the 2 points. But I think in general, in 2 dimensions, most often you're going to find 3. But if you have more than 2 dimensions, you can find more than 3 support vectors. But you can always think of the extreme case where your data set only has 2 points. So in that case, the support vectors will only be 2. So to sum up this part, this was a bit confusing, but the basic idea here is that we had this original problem of trying to maximize the margin to reduce overfitting. We cannot solve this problem directly because maximizing the margin requires maximizing the distance to the closest points, and the closest points change as we change the position of the discriminant. So this makes the function have those straight edges, and we cannot solve it numerically. So this is why we get into this more complex mathematics for the support vector machine, and what we end up is with a constraint optimization problem that we solve using these Lagrangian multipliers for the constraints. And the constraints are that all the points must be at least 1 unit measured by the vector of our discriminant, 1 unit away from the discriminant. So this is the size, the minimum size of the margin. If we have only 2 points here, then we don't have, it's not determined the direction of the discriminant. In that case, we have lots of different solutions that give us the same value, and the discriminant can be any of those. So in this case, what we are looking at is trying to optimize by minimizing the size of the vector we have here, but forcing this constraint to be true for all points. Now, this constraint of the margin is trivially true for all points that are away from the discriminant, but is really problematic only for those support vectors, which are those that are closer to the discriminant. And that is the basic concept here for the support vector machine. Those support vectors that determine where the discriminant lies are those that have alphas, the Lagrangian multiplier, larger than 0. Everything else is irrelevant, and the Lagrangian multiplier will be 0. So why do we go through all this bother just to have something that is a linear classifier? Actually, this shape of the support vector machine has some very interesting properties that we're going to look at in the next lecture. So this lecture was a bit painful, but it's important for you to understand these parts, so these inner products here, the Lagrangian multipliers, these constraints, because now we can proceed from here to forms of regularization and to going beyond this linear classification very easily with some small modifications that we're going to look at after the break. So let's take a 5-minute break, and I'll continue at 5 minutes to 5 with the second part. So see you soon.